Howdy. So we're ready for Chapter 16, Fundamental Chemistry 2. I've got a guest with me today, my junior lab instructor, and well, my safety inspector is down here as well. So we're ready to do carbohydrates, and this is a sweet, sweet chapter. So our learning objectives on this chapter, we'll be looking at we want to know the classes of carbohydrates, being able to look at stereoisomers. Most of this chapter is going to be about learning how to identify the different types of carbohydrates. Okay, so looking at this chapter, we've got monosaccharides, which are saccharin. Saccharides means sugar, so they mono means one. You guys should know that by now. Di being two of these, and then oligo being many or a few. So 3 to 10 is what we're looking at there. And then when we get to polysaccharides, we'll be looking at highly branched, and so that'll be more at the end. Okay. So the first skill we want to learn is this idea of aldose versus ketose. So I've got two sugars here, and we'll be playing with these sugars, and it's really just about, is the most highly oxidized carbon an aldehyde or a ketone? And you'll notice it's usually CH2OH here. So a couple of things that we'll notice about our sugars, we've got some kind of carbonyl, and we've got all these OHs, so we expect them to be extremely water soluble. And the CH2OH at the end is kind of systematic, but it's really then an aldehyde is an aldose, and if it has a ketone, it's a ketose. And so I'll show you a picture, and you tell me, is it an aldose or a ketose? That simple. There's really nothing difficult about those. Now, when we get into different drawings, you're always looking for the most oxidized, which will be our carbonyl. All right. The next way that we classify these is based off of our don't be in charge of clicking this, or don't worry about it. Is to count the carbons. What's that? Anna can try to get out?
Yeah.
That's all right. And so counting the carbons, you're just going to count mono, di, tri. And so all of our start with tri, tetra, penta, hexa. We've seen these prefixes before. So you're just literally going to count the number of carbon atoms. So one, two, three, four, five carbons, right? Don't forget you've got one at your carbonyl. And so 5 would be a pentose, all right? And it's that simple. Now this particular one is an aldehyde, so it's an aldose and a pentose. And we can combine this idea by taking that, calling this an aldopentose. Okay. So not very difficult. We just want to be able to look at a structure, count the carbons, and tell if it's aldehyde or ketone. Okay. So as we're doing these, let's get a few more examples on these then. Let's do this one. You want to help me on this? how many carbons? It's got 1 there, 2, 3, 4. There's not one at the end, so it's got 4. All right. So if I go back a slide, OH helps make it water soluble. That's all it's for. All right. All right. And so 4 would be tetra. So this is a tetrose. Okay. And then it's got carbon, carbonyl. That's this double bond thing here. So carbon, carbonyl, carbon. So that's keto. So we put keto tetrose. That would be its 2 classifications put together.
Keto tetrose.
Keto tetrose. It's a fun name. All right. So I'll draw these and we'll classify them. And does it make it super difficult? We'll see some of these in other drawings, and we'll learn about these drawings as we go. But this one's an aldehyde, and it has 1, 2, 3, 4. So aldehydes have aldo, and what was 4?
4 is tetra.
Tetra, and so it'll be an aldo tetrose. Okay. All right. So see if we're ready for a tougher discussion here. This tougher discussion being that on stereoisomers. And so stereoisomers we've seen a little bit when we had our cis and trans. Those were this idea of diastereomers. And so playing with stereoisomers, playing with these, it's a little bit tough because of some of the new definitions. So we want to look at our term superimposable. Superimposable. All right. And so I'm going to take 2 models here. Now these models, they have 4 different things on them. So each one's got a green, a blue, a yellow, and a red. All right. And so it helps if we put the models where you can see these. So each one's got green, a blue, a yellow, and a red. So playing with these models, they spin around, and so we want to know if they're superimposable. If they're superimposable, I can line them up to where they're in the same coordination. Can you line those up? To where the green would be facing the same way? So the yellow's on top. So if green's facing you, like that. Do those match?
Yeah.
Is it superimposable?
Yes.
Yes. All right. So now I'm going to make a little small change. All right. Now, can you line them up?
No.
No. Put the green on top. Put the yellow on top. I'm sorry.
Wait.
Do those line up?
Yes.
They are? They are? The red is here and here?
Yes.
So if I get these a little bit closer, you can see that the red and the blue.
Oh.
You got 2 of them, but not the other 2. And so if I mix them around, sure enough, they're not superimposable. And that's the idea of stereoisomers. And so these have a very special relationship. They're actually mirror images. And so if I were to hold these up, let's try and go a little bit bigger here. If we hold these up, we can see that I can hold the greens next to each other, and then the reds line up, okay? And so looking at these, if I were to draw a line here between them, you can see that the greens are equal distance to the lines, the reds are equal distance, the blues line up, and then the yellows up top line up, all right? So these are mirror images. And then they're not superimposable. So we're going to say not by saying non-superimposable. Okay? So they're non-superimposable. They have mirror images. So these have a fancy word for them. They're called enantiomers. Enantiomers. Fancy word for not superimposable, and they are mirror images. Alright, so these are enantiomers. Now, we have another type of compound here, and that's diastereomers. Ooh, trying to read my handwriting? Instead, we'll look over here. And so diastereomers are not mirror images, but they're also not superimposable. Okay? Now, if they were superimposable, they're not stereoisomers. Okay? So now we're going to look at what we've looked at in the past, back when we did alkenes and when we did our green structures. Anytime we lock in the carbon so that they can't spin, we look at things like this, where we had cis and trans. So pick up our cis. Remember, we've got our double bond. They're locked in. The two big things are on the same side of our double bond. We had trans, where the two big things were on the opposite side. I'll remind you, a lot of students prefer to think of this. This is cis, right? And treat the shape as a C. You see the C? All right. So these are on the same side, and let's play with them a little bit. So let's let you actually hold them. Can you line those up to where they're the same? Hold them up high, where everybody can see. There you go. Can you line those up where she's spinning and twisting? Is there any way to make them the same?
Exact same now.
Yeah.
Yeah.
No. So what can we say about them?
They're
Non-superimposable. Good. So they're not, the big words, yeah, lots of big words for they don't match. They don't match. That's really all we're saying. Is these don't match. They're non-superimposable. All right. So you've got to memorize these terms. Lots of fancy words. All right. So our fancy words then, diastereomers. They're not mirror images, but they're non-superimposable. Enantiomers, they are mirror images, but they're non-superimposable. All right, so looking at these fancy words then, one of the things that was special about enantiomers is it took place when we had a special kind of carbon. And that special kind of carbon is called chiral. And so a chiral carbon has 4 different things on it. And so if I go back and I play with my models, and I replace a couple of the things on it. So I'll take the yellow and the blue off. Hydrogen down, it's gone. Clearly my surface is not level. Oh, there you go. It'd help if I'd taken the same ones off, huh? What did I take off here? So I got blue and green. We need green back on this one. See if I keep the sticks in, they don't roll away. Fancy. Alright. So now they don't have 4 different things. Remember the last ones had 4 different things. They had blue and yellow and green and red.
Yeah.
Now I've got 2 whites on each one. So I'm going to make mirror images. Right? So they're mirror images. right? This, no, they're not.
No, it's not matching.
Right? Can I do it? Oh no. How about that? Is that a mirror image?
Yes.
Okay, good. So they match. These line up. Those line up. Across here line up.
Mm-hmm.
Oh man, nobody's able to see anything we're doing. All right, here we go. So we're making these mirror images. We're making the hydrogens line up across here, hydrogens across here, greens and the reds. All right, so they're mirror images. Now, I want them facing the same way and to line up. In other words, can you make them superimposable?
Let me see. So you want me to make them?
Yeah, go ahead, pick it up and pick up one. Don't pick up the other one. Just pick up one. See if you can spin it, twist it, do whatever you need to do to make it superimposable.
That's just a mirror.
That's still a mirror.
Huh.
So first thing, you got a white on top. So we want a white on top,
Mm-hmm.
but we want the green over here. Can you do that?
Yes. Both the green over
No, you're back to mirror image. I want a white going that way. There you go. Ta-da. What'd you do?
I flipped it.
You flipped it. You tilted it over on its side. And we could do that because we had two whites. All right? And so this is not chiral. And so we can flip it and alternate between it. As long as we have two of the same things, we don't have to worry about enantiomers. So chiral is this very special case where we have 4 different carbons. All right? 4 things on the carbon. And now this means that we've been having chiral carbons all of the time. This one, let's put a thing on it, and we're going to look at what's on each one. Now, we're going to have to teach you real quick how these drawings work. Each carbon is at the intersection of the lines. All right? So here's a carbon. It's at the intersection of those lines. There's actually a carbon here, and each carbon has 4 bonds on it. So these have
8 bonds.
So this has 2 hydrogens since we're missing 2 bonds. This one's only got 1 bond shown. So this carbon here has 3 hydrogens on it. And this one has 2. There's a carbon there. There's carbon here has this. This carbon, it's got 2 bonds to an oxygen, and then it's got an OH, and then 1 bond over here. All right. So we're going to play with this picture, and we're going to learn. This one's got how many things on it? Well, it's got an oxygen, another oxygen, which is different than that oxygen, right? Because this one has an H on it, right? And then this, it has a carbon. So how many things is that? Well, it has an oxygen, and it has an oxygen that has an H on it, and it has a carbon. How many things is that?
That's 4.
Is that 4?
Wait. 3.
3 things. So is that?
Letters.
You're fine. Is that? Can that be chiral?
No.
No. So that's not chiral. All right. So we don't have to worry about it. This one's got 3 different H's on it, and a carbon. It's got H, 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 and carbon. Is it chiral?
Yes.
It has
Wait.
4 different things.
No.
No. This one's got a carbon here. Now this carbon is actually different than this carbon. This carbon has 3 H's. This carbon has 1 H and a bunch of other stuff. So those 2 are different, but these 2 H's are the same. Can it be chiral if it's got 2 H's, 2 of the same?
No.
No. So now we're going to look. This one's got 3 H's. We know it's not chiral. The only one that could be chiral is this one. Let's make a list. It's got a CH2CH3. That's this side. All right. It's got an H. That was a terrible 3, by the way. 3. There we go. It's got an H. All right. Now it's also got a CH3. And then it's got all that business, which is, we'll just write it out since it's so different, a COOH, which is, that's an acid group. Okay? So, does it have 4 different things?
No, those are 2 O's, 2 oxygens.
Is this the same as any of those?
No.
Is that the same as any of those?
No.
Is that the same as any of those?
Mm,
So, does it have 4 different things?
Yes.
Yes. So what's it called?
A
Chiral
car.
carbon.
I can't think on
That's fine. It's a chiral carbon. We also call it a chiral center. All right. And so on these, it can be a little bit tough to pick out which ones are chiral carbons. So I'm going to do, let's go to this one. And so we get a little more practice. And so this one's got 3 H's on it, right? See them?
Mm-hmm.
So that can't be chiral. This one's got 2 H's. That's enough to not be chiral. This one, I've got a couple different places. This one, does it have, it's got 3 H's on it, right? It can't be it. This one's got 2. So I'm really only looking at that one right there. That's my only one that could be chiral. It's got a carbon, another carbon, and another carbon, but they're not the same. So it's got an H attached to it. It's got a CH3 over here, so I've got them numbered, right? So this is number 2 over here. And then over here it's got a CH2CH3, which looks a lot like this one. This is a CH2CH2, but because this has a Cl, it's different than that one.
Alright.
So sometimes you have to go a bunch of carbons away. If there's any difference at all, they're different. Alright, so finding these chiral carbons can be a little bit tough because sometimes you got to go far out there. Alright, so let's see what we got. Here's our picture of our doing the same thing that we were doing, of spinning these and making mirror images. Okay, so we did that with the models. Alright, so we're ready then to change how this is drawn. And so when we draw these, if we were to draw our zigzag pattern with some chiral carbons, that one's not chiral. But if I make this one chiral, I have to use a pattern like this to tell me, hey, this H is coming up out of here, right? So it'd be sticking out kind of, it would be where this red is. So let me put it to where people can see what we're talking about. There we go. So this H goes back, all right, and this H coming out, which would be like that yellow. See that angle that yellow's at?
Yes.
The green. I'm sorry, I keep saying yellow. How would you describe the red one?
Red one is.
If I make the black one and the 2 white ones flat with my board, how would you describe the red one? Is it coming out of the board, or is it going down into the board?
Coming in.
You're looking at this is flat. This comes up, and this one comes down. So that's the one going down, and this is the one coming up.
Yeah.
All right, so we have to draw to show this is a chiral carbon, and we would have to draw these stereoisomers like that. All right. Now, if this was organic class, we would worry about describing if this orientation was something along the line of R and S. And so sometimes when we see a big long compound that has chiral carbons, they describe each orientation around each one of these as being R or being S. And so you might see something like 3R and so on and so on. All right. And so this R and S is done by assigning each of these an order, and it's based off of their mass. And so they get a priority. And then you put the lowest priority away from you, and you would describe this one whether it was R, if it went right or left. So this one would be S. Okay? We are not going to worry about any of that. We're worried about how the stereoisomers affect our sugars. And so when I draw this sugar, I want to quickly be able to see that these lines that are going horizontal are going to be wedges. They come out. That means the other line, so if I look at my carbon and I got 2 of them coming out, these 2 are going up. Where are the other 2 going?
They're going down.
They're going down. And so if we're trying to draw this on a flat piece of paper, normally then we would have to put dashes. That means those would be going down, this would be going down, and this would be coming up with wedges. All right? And so this projection is always done the same way, where you put the most oxidized carbonyl, in other words, your aldehyde or your ketone on the top, and then we are going to align things so that these ones, the wedges, coming out. Now that means we'll get stereoisomers where we can have this carbon here is free to rotate, but now I can look at whether things are mirror images much easier. Remember, this one is free to rotate. In other words, if we could spin along that, it's not stuck. It won't put things in different order. Why? Because it has two different things. And we saw when we had two different things, we could spin it and flip it, right? But here, we can't flip here. Notice, just looking at my chiral carbons, that's these that have these cross parts. Those are my chiral carbons. That those are these mirror images?
You can't tell.
Well, yeah, see this lines up, and that lines up.
Okay.
This is on the part, and those are mirror images. How did I tell? I drew a line between.
Oh.
Okay. Now, I want to imagine. Can I pick this one up? If I move it on top of this, will they be the same? Will this OH match what's over here? No. So if I slide this way, like if I had a piece of paper that had that drawn on it, and I put it on top of this, and tried to look through it, would I be able to see it? I mean, they can't see it. They can't see through the paper. All right? We can see through the paper, but they can't. All right? So if I look over here, then they wouldn't match up. Okay? Now, we might say, what if I just flipped it? Right? So we're talking this motion, flipped the compound. And when we draw them flat, yes, they would. But when I've got one of these, and we've modified them all, so we got 4 different things on it. All right. So I'm gonna put the green and the red going down, and these. So that's these. I'm sorry. And they'd be coming up, right? The ones that going across come up. So if I take this thing and I flip it like that, what happened?
They're going down.
Now they're going down. They don't match our drawing. All right. So when we have mirror images here,
It's easier.
then they're non-superimposable. Do you remember what that word was? For things that are not superimposable and are mirror images, those are enantiomers. Enantiomers. All right. Fancy words. Don't worry. Everybody's going to have to study those. All right. So these drawings can be a little bit tough. Let's get some of these pictures. Not too far back. All right. So now this Fischer projection allows us to do a couple of things really nice, really easy. We can see mirror images easier. I can also tell real fast how many carbons are here. So I'm going to count them. Here's 1, 2, there's 1 at this intersection, 3, 4, 5, 6. So 6 was hexose. And then I can also look up here at the top. It'll always be the most oxidized will always be at top. So I can look up top and see if it's got an H on it, like this one. It doesn't have anything, so that would have an H. All right. But this one's got 2 bonds there, 1 bond here, 1 more bond to a carbon. It's got a carbon, so that's a keto. So this is a ketohexose. Makes it much easier to see just up top. Here's an aldose, and it had 1, 2, 3, 4. That's our aldotetrose we saw earlier. Yeah.
Really need an easier system.
Wait till you get to some of the fun stuff. All right. So this one, we can also see how many chiral centers it has. All right. So a chiral center was a thing that had 4 different carbons. So I might ask, how many chiral centers does it have? All right, and that's these places that go across. And so this has 1 there, 2, and 3. 3 different chiral centers. Because this has a C to an OH. This has a C that has an OH, but it has all the rest of that, which is different. And this has, so you can really look at it as the top and the bottom are different. And if the top and the bottom are different, each one of these is chiral. Notice this is a carbon, but it's not chiral. It has 2 H's on it. 2 of the same thing, enough to make it not. Notice this bottom one, we always see this kind of looking tail. It has 2 H's. It's not chiral. That's why we didn't draw it across. So we don't ever draw anything that has 2 of the same thing, because that's not going to be chiral. So Fischer projection is just about being able to see these. Now I always like to remember the name. It kind of looks like a fishing hook on the bottom.
Yep.
You tie it off here, and it's got this hook on the bottom.
Tailfish.
Yeah, and so it's gonna. That's what a fisherman's gonna use. All right. So Fischer projection, nice and easy to see these. So we want to learn a little bit more about then what we're going to be drawing these. All right. So we can draw the mirror images just like we were doing before. So if I want to draw an enantiomer, I just draw a plane, and then I draw a copy over the H, copy over the OH. So let's practice one of those. We want this to go screen, white screen. All right. So we'll draw one. Let's do our Aldose tetras we liked. Now, it doesn't matter which way this one goes, but we'll go ahead and draw it. All right, so first step, that's our mirror. So when you look in the mirror, you ever notice when you look in the mirror, your right hand is on the left side?
Yep. So you got a mirror that.
Yeah, we got a mirror. So I'm just going to see how far that is from the line. I'm going to draw that about the same distance. And then it goes away from the line, so we'll go that way.
May I try?
Uh-huh. You want to draw the rest of it?
Sure.
All right.
There's a bit more.
Okay, and then it goes which way?
And it goes this way.
Okay, straight line.
I can't draw that straight.
Just draw quickly. There you go. Then what's on down here?
OH.
An OH, but the H will be close to the line. So there you go. And then we got 2 things going across. So go ahead and draw those 2 things. And then another thing across. Now, which is, this one's close to the line, right? OH. And so here it's going to be.
Right there?
Uh-huh. And OH. Put the O on next to that line.
I understand.
Yeah, like that. And then this OH, is it on this side or this side? Well, we want it to be close to the line, so close to the line over here.
So it'll be.
There you go. And then what's on this side? What's far away? The H's. Draw your H's. Capital H's.
Oh, well.
That's all right. Good enough. Good enough. Good job. All right, so that's how we draw these enantiomers. You're just going to copy them over on the mirror images. All right, so playing with this, we have all these enantiomers, and that's how you tell the different sugars. But each sugar really comes down to classification. Instead of worrying about each one, whether it's R and S, we classify carbohydrates based off of D and L classifications. And so this is one that always caused me trouble, but it's really easy to tell in Fischer projections. That's why one of the main uses of Fischer projections is we can tell just by looking at the bottom chiral carbon, the last one that goes across, right? And it's D if that OH is on the right hand side, it's L if it's on the left hand side. So L for left. All right, so let's draw a couple. Let's draw a couple. Now it doesn't matter what's going on up there. Doesn't matter what's going on here. It only matters what's going on Where?
That is a D.
It's only on the bottom chiral carbon. So this one, we're looking at this OH. Good. And you said it's a D because it's on the right.
Yes.
Yes, it's a D. And so if I drew an enantiomer of that, it would be L. Or if I just drew the same thing and switched that last one, it would be, so I'm going to switch that last one. O, H, 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 H. Terrible H's. There we go. Good enough. Is that D or L?
That's L.
That's L, because this is on the left-hand side. Okay? So when I go and I make a sugar, if I'm making it in the lab, I have a 50-50 shot of doing it. If I go and I make some big long sugar, oh man, what's going on with this sugar? It's got a lot. Let's see what we can describe about it.
That is a D. It's a D.
It's a D? Why?
Because the last.
Point to the one. That one. Yeah, so this one makes it D. This one makes it aldose.
So, and there's 1, 2, 3, 4, 5. I don't know.
No, there's 1, 2, 3, 4, 5. There's 5 chiral carbons. Good. And the first thing we started with, how many carbons are there total? Well, there's 1, 2, 3, 4. We're missing an H. Should be an H there. There we go. 1, 2, 3, 4, 5, 6, and there's one there. 7. All right, so we had 7 carbons. 5 of them were chiral, but there's 7 total carbons. All right, and 7 is hept, and so it's a heptose.
So aldose heptose.
Aldoheptose with D, and we put D out in the front as a capital letter, and then put a dash. So it's a D-aldoheptose. And I will give them a picture, and I'll ask all kinds of questions. So we'll have one question I might ask, is it, now if I ask aldose or ketose, then that's 50-50 shot. So we're not going to do that. I'll ask aldoheptose, or I'll say ketoheptose, or I'll say aldohexose, or aldotetros. I'll pick some others that are wrong, right?
Aldose tetras.
And so when I do these, they'll do multiple choice, be able to pick those, no problem. All right. And then I'll also have a question when I say how many chiral carbons, and then I might just say, hey, is it D or L? Or I'll have the D and L mixed in with some of the others. We are recording.
Oh, well, we just broke the fourth wall.
Why? I tell them that's what how they're gonna make that test. That's what that test is gonna look like. All right. And so it's just a matter of learning. Should be that way. How to interpret these drawings. D or L?
I still have to look at the screen.
What do you got to look at the screen?
It has to.
Oh, it has the instructions on it. Over here? Yeah. So that's fine. They're gonna memorize it. But let's put it on our note. L is OH on left. That's how I memorize it.
Okay.
All right. So
that's L.
That's L. Which OH are we looking at?
That one.
The bottom chiral carbon. Good. How many chiral carbons does it have?
2.
2. 1, 2. Good. How many total carbons? 1, 2, 3, 4, 5.
So 5 carbon is
It's pent.
So
Pentose. And then this is a ketone
So
because it's got
ketose.
a carbon on the other end of there.
so L-ketopentose.
L-ketopentose. And that's how we classify these, all right? So I'm worried about us classifying them. There's a whole list of these that we could memorize and go through and get a list of all of these that we memorize. So we could classify, let's see if I have a list of these way down here. Here's a big list of sugars. All right, and there's all these sugars, and they go through all the possibilities. So this one had 3 carbons, and it's on the right-hand side. And this one had 3 carbons, and they did one where they had both on the right-hand side, and the next one, it had one on the right, one on the left. Now, is this one D or L? Oh, man, let's make this a little bigger so that everybody can see. All right, you can't see it on that. Yeah, it's a terrible picture, man. You know why it's a terrible picture? I stole it off the internet. Don't ever steal stuff off the internet. Let's go way down to this list. There's a list of sugars I stole off the internet. Terrible. Oh, it actually looks better on the projector.
First class plagiarism.
That's right. That's right. Now, if you're a teacher, it's called free use. It's not actually plagiarism. Now, what I should do is say where I stole it, but
where's the fun in that?
there's the fun in that, so I guess it is plagiarism. All right. Now, which side is this on? Is that on the? Is that D or is that L?
That is. You erased my thing.
I erased your definite L was L for left, right? That's how you tell your left hand side.
It's a D.
It makes you hold up your finger. Your left finger makes an L.
It's a D.
It's a D. All right. And if I look, it says D right there, right? If we look, all of these are D. It's sneaky. So why? Why are all of these D? It turns out, sit down so they can see. It's all right. So when we're doing these, if I make them in the lab, it's 50-50 shot of getting D or L. But when these are made in nature, they're made one atom at a time and made real specific places, and we almost always get D. That's why all of these on this table are D. We could do L's. All we have to do is swap the bottom one.
So L's like the ugly duckling.
Ugly duckling. All right. We make a couple of them, but it's almost always D. Okay? And so we could, and it has to do with how it lines up. It's that last one they put on. So all this table is, the way you would generate it is all of these want to be D, so the bottom one has to be to the right. Okay? So this one you start with both of, this one you only got one chiral center. Here they just added another chiral center. All right? So notice as I generate this table, these are all aldoses. And so these are the names, these are all aldoses. There's another table that's all ketoses, and you make it with one. And so if we wanted to memorize all these names for all these sugars, you would learn how to draw this table, and you would come up with some fancy way of taking this G and E and T, and you would come up with some way to memorize the starting letters so you can memorize it. Guess what?
We're not doing that.
We're not doing that, and somebody wants to do that. If you want to memorize these, go to YouTube. Find somebody that came up with some fancy way of memorizing it. Oh man, there's got to be some mnemonic that you can use. We don't care. We really don't. We're going to be looking at these and saying, hey, this is an aldotetros. No, an aldotrios, right? And it's D. And when I come down here, I'm not going to ask you to tell me that that's D-mannose. All right? And I don't care. I want you to tell me it's D, and I want you to tell me 1, 2, 3, 4 chiral carbons, right? 6 total, so that's an aldohexose. And that's how we'll be asking questions on these. So I'm not interested in memorizing the names on these. So we're doing these. We want, which picture? we're doing these. So we also have this idea of racemic mixtures. Now, a racemic mixture, what happens with the D and the L is they cause light when they pass through it to go different directions. It spins the light different directions. All right. Now, so if I have one that spins it to the right, and then I have one that spins it to the left, what if I have equal amounts of both of those?
It'll stay in the center.
It'll stay in the center, and that's called a racemic mixture, where I have equal amounts of the D and equal amounts of the L. And so I'll have a 50 mixture. It won't affect light. All right. But everything else, if I get all D, it'll take it right. It'll take it left. Now, we can have instruments that we can use for that, and we can assign those. We're not too worried about it. But you can tell, if you have these sugars and you make a solution of it, you can tell one of them apart from the other.
One is transparent?
No, it's not that it's transparent. You shine light through it, and it rotates the light. Now, how do you shine light to where it only goes? You remember 3D goggles?
Yeah.
You know, when you go to the movies?
Mm-hmm.
All right? And so one of your eyes has, you know, how they kind of get dark, kind of like sunglasses. It's because they're blocking some of the light. One of them only lets light that's going up and down. And the other one only lets light that's coming in at the side. And so if I put one of those in front of my light bulb, and so only the light going up and down goes through it, and then I put my sample, and then on the other side I put a filter where only up and down light goes through. If that sample rotates the light, what I have to do is I have to rotate that until I find and line it up with the light. So now I get a bright spot where it's coming through. But if I misalign it, I don't get any light come through.
Okay.
All right. Now sometimes you have to turn it left, and sometimes you have to turn it right to figure out which way the light spun. Did it go right? Did it go left? And so we have a fancy instrument that does just that. It shines a bright light bulb through it, and it's got a filter that only up and down light goes through, and then you figure out how much it rotated. But a racemic mixture is 50-50.
Okay.
And so it doesn't rotate the light. All right? All right. So we had our D and our L. We're ready for multiple chiral carbons. All right? And so let me blank this screen. Make sure we go white. All right. So there's a way of keeping up with these to figure out how many enantiomers there are. And so all this is saying is we can look at these and say this has 2 chiral carbons, and so there's 4 different possibilities. All right, and so there's this one on the left, and when I draw its mirror image here, see how those 2 are mirror images? Don't worry about the top and the bottom because you can spin those. It's only the chiral carbons. All right. And so those are mirror images. And then here, these are not mirror images to these. They're a different set. All right? So this says 1 and 2 are enantiomers because they're mirror images. What do we call it if they're not mirror images?
They're
now I can't non-superimposable. Now they can be either superimposable or non-superimposable. All right, so you want to play something? You can play that. This is chemistry. We don't play the dog toys. All right, so here we've got these are all non-superimposable. How do I tell that? I try to pick them up and I move them on top of the others. And so I imagine coming in and grabbing one and moving it on top of the others. Okay. So when I'm looking at these, does that make that better? Nope, just tough to read on these. All right. So when we're looking at these, I'll give a set of 4 and I'll ask about these, and so you need to be able to draw a line between them and see if they're mirror images. So 2 and 3 are not mirror images. You want to take a break?